37. It is observed that the reaction producing potassium chloride from its elements goes essentially to completion. Which of the following is a true statement about the thermodynamic favorability of the reaction? Okay, so this time we're talking about all these like delta H and thermodynamic favorability. We're talking delta G Gibbs free energy. So the equation you want to be thinking is a thermochemistry reaction. Delta G is equal to delta H minus T delta S. Remember, you would like the delta G to be negative in order to have it thermodynamically favorable. So right now, we already know that this reaction is exothermic process. So that's negative sign for the delta H minus this T. Remember, that's temperature in Kelvin, right? And Kelvin is an absolute temperature. A lot of people actually don't know what that means. What that means is like absolute temperature, like absolute value. It turns everything into positive. Absolute temperature just means a temperature that can never be negative. And if you guys think about Kelvin, there's no such thing as negative Kelvin, right? 0 degrees Celsius is 273 Kelvin, right? So negative 273 Kelvin is essentially the lowest ever freaking temperature that we can ever achieve on this planet. So yeah, long story short, that delta T must T value must be positive. Now, what's happening to the delta S, the entropy? Well, we have a solid and gas turning into a solid. That's a decrease in entropy. Remember, what is entropy? Disorderness, chaos, right? And now this thing is becoming more organized, less disorder, which is why the delta S sign is going to be negative. And check this out. That negative, so let me kind of highlight it. The negative and negative will turn that into positive. So you have this negative plus something, right? It's this positive thing. And remember, we want this delta G to be negative, so adding that thing is really not something good. That doesn't really help your delta G to become more and more negative. In fact, it's more likely to make it positive, which is a no-no, because if the overall delta G value is positive, that's thermodynamically not favorable, right? So in this case, yes, if the reaction were to go to completion and therefore it is thermodynamically favorable, that is probably, well, it is favorable because it does go to completion. So that's already an indicator that it is thermodynamically favorable. So we get rid of B and D. Now, why is it favorable? Driven by enthalpy change only versus enthalpy and entropy. Like I said, entropy is not helping right now. Entropy being negative is not helping, so that's why C is out and A is correct. Remember, if you guys refer back to some of these, always exothermic, always endothermic reactions, right? Something that is exothermic with increasing entropy, that's always thermodynamically favorable. And something that is endothermic and negative entropy, well, that's never, ever thermodynamically favorable. Now, I do want to say one thing about this problem, because some people have a hard time memorizing that fact. I really don't recommend you to memorize that. The easy way to think about it is like this, right? Think about exothermic process that is increasing in entropy. Well, wildfire, right? It's not like you have to, spread the fire in order to get that wildfire going. It just kind of happens because it's so spontaneous. Well, spontaneous just means thermodynamically favorable. That's what we used to call it back in the days. So yeah, as you can see, anything that is exothermic with increasing entropy, well, it's very, very likely to happen just by itself. Now, on the other hand, if we have an endothermic reaction with decreasing entropy, what's a great example of that? You cleaning up your room, right? I mean, we all don't like to clean up our room, right? Because it takes energy, aka endothermic process. And when you clean up your room, what happens to your room? Well, the chaos, the disorderness decreases. It becomes more organized. But are we willing to do it? No, we're never willing to do it. So yeah, it's like never spontaneous. It's never thermodynamically favorable. I don't know if this makes sense, but that's how I like to present to my students.